Hello.
So, we introduced chemical equilibrium last time, and I started to link this to many of the concepts we have discussed this year. And I don't want to go through every single one because it will become extremely overwhelming. But big idea 6 is listed right here, and I had mentioned this last time. And at the end of this lesson, or at least the group of lessons that go in this chapter, you want to understand that chemical equilibrium is a dynamic process, and you're going to look into initial conditions as well as any type of factor that can affect equilibrium and how the system reacts to those factors, otherwise known as external perturbations. That's hard to say. All right, all the learning objectives, and you can see there's just a slew for equilibrium, acid bases, solubility equilibrium. That's why I don't go through every little piece, but I make sure we hit them all. And there are a lot that we have covered this year, and we will make sure that we have hit every single one so you are overly prepared for your AP exam, which is May the 1st. So it's not that far off now. It's getting closer and closer. All right. Last time we reviewed or learned how to write equilibrium constant expressions where you have KEQ is equal to products over reactants. Now if you're talking about concentrations, it's KC. When we get to pressures, it's going to be KP. So you'll see that today. Before, yep?
Why do we exclude solids again?
Solids and liquids have constant concentrations, if you will, and in regard to pressure, you'd only be dealing with gases there. You don't really see any alteration in their concentration, so they're not included in KEQ expressions. It deals also with activity, but different from the activity series, but we'll come back to it in a little bit. All right. So we want to look at how equilibrium constant expressions can be modified. And at first you're going to be like, ooh, this looks like Hess's law to an extent with one major, actually two major differences. So be careful here. Sometimes you like to draw these similarities and they're good, but in this case, be careful. All right. When we reverse a chemical reaction, we're going to inverse the equilibrium constant. That is to say the reciprocal of it, not the negative of it, because we know KEQs are positive values. Okay? So for example, if you show the formation of nitrogen dioxide from nitrogen monoxide and oxygen gas, Kc given right here, and this value is considerably larger than 1. Let's focus here on the green first. I'll go over the letter designation in a minute. If you look at the reverse reaction where nitrogen dioxide is the reactant and these two substances are the product, when you want to know its Kc, you simply take the inverse or the reciprocal of what you started with, and you could calculate that out. Now without a calculator, you might be dealing with letters. So if this is A, this is 1 over A. So when you reverse the order, you simply take the reciprocal. Yes? Mm-hmm. Okay. When the coefficients in an equation are multiplied by a common factor n, and be careful here, I'd say for simplicity, n is going to be a number like 2, 3, 4, etc. Don't really see it being a fraction because that would really get complicated as an exponent, because then you would, yeah, I don't think so. I think it's just going to be 1, 2, 3, 4, etc. All right, so if you're looking again at the formation here, you have the same Kc, but to go from this equation to this equation, well, I guess you could go fractional then. So I take that back, you could. So to go from here to here, what did you multiply by? A half. Did you change the order? No. So you multiplied by a half. So now the Kc is raised to that multiple, which is a half. So kc to the 1/2 power, you take the square root of. Alternatively, if this is a, this would be a to the 1/3. So if you had this expression and you multiplied by 3, a would be to what power? Third. Easy, easy? Here's the other new piece right here. Actually, here's an example, and then I'll show you for a net reaction. It says the equilibrium constant for the formation of sulfur trioxide from sulfur dioxide and 1/2 mole of oxygen gas is 20 at 973 Kelvin. And again, the temperature must be specified because temperature is the one factor that alters the value of KEQ. Calculate Kc at this temperature. What did I do from here to here? Right. So not only did I multiply by 2, but I also flipped the order. So when I flip the order, I take the reciprocal, and because I multiplied by 2, I have an exponent of 2 here.
Does it matter which one you do first?
Probably not. Let's think about that. Let's say you started with 8, all right? Let's not use 8. Let's say you had 16. He's saying, does it matter what you do? I mean, here I did it all at one time. But let's take a look at that, and let's just use. No, it's not gonna change. But let's take a look. So let's say Kc was equal to 16. Okay. Let's say we flip the order. Then K prime C would be 1/16, and let's say that we are going to the 1/2 power, okay? So K double prime C would be this to the 1/2 power, so the square root of 16 is what? 4. All right? Let's say we did it the other way, where we did the 1/2 power initially. So we'd have 4, and so it will stay the same. So the answer is no, but it's good to prove it, because now you know, and it doesn't matter what you do first, and you'll be happy. Okay. The equilibrium constant for a net reaction. Remember in Hess's law, you added all the equations together, and if they added out, then you could add out the delta H's. In this instance, you're also going to add out all the equations the same way, but instead of adding those KC's, you're going to multiply them. So there's the key difference there. So there are similarities, but there are a lot of differences. So be careful. And these two chapters are tested together. So it can be a little bit tedious. Just stay on top of it and you'll be fine. All right. So what we're looking at here is we want to calculate the equilibrium constant for the following reaction, and that's shown right here. We've been given these two equations. I'm looking to see if it's set up properly. I start at my first reactant, just like with Hess's law. I see it right here, suggesting reaction 1 is written in the correct order. Since the coefficients match, it appears that I don't need to modify this equation in the least bit. Similarly, product matches, coefficient matches, I'm looking good. These two substances cancel. They're on opposite sides of different equations with the same coefficient. These two substances are on the same side of the equation, so I'm going to add them. And this is 1 1/2, or 1/2 plus 2/2 is 3/2. So these add to be this, so then I multiply the Kc values shown here. In regard to math here, let me show you a few things that I'm sure you are aware of, but a little review never hurt in regard to math that you probably learned 3 years ago. They gave us 1.7 times 10 to the negative 13, and we had 4.67 times 10 to the 13. Now, if you didn't have a calculator, you're not going to sit there and multiply this in the margin like you did in, you know, 3rd, 4th, 5th grade. You're going to make this 2. Well, yeah, that's going to push it over. So it's a little tricky. You can make.
You can multiply 4.7 now.
You want to do 4.7?
You can multiply 4.7.
Okay, fine. The only, I didn't want to push it over 10 because that's going to change everything. So this times this is what? And when you multiply, what do you do to the exponents? So what do you get? Well, 10 to the 0, right? Which is 1. So that's going to be about that, correct? Something like it. It probably is going to be a little less because we up this, and that's what you're getting here, all right? So make sure you can do math in your head. When you multiply exponents, you add them. When you multiply 2 expressions with exponents, you add the exponents, okay? When you divide expressions that have exponents, you subtract them. All right. Let's take a look here. It says use the following to calculate KC. You want to do it together or you want to try? Try. Go for it. I'll try too. And this stuff's all fun and it's mathy and some of you will be much happier. How do we do? What'd you get? I went one person at a time. Oh, did I give W's and X's? Oops.
Well, yeah. It could also work like that.
You would have W over X squared. I agree with that. I did them with KC1s and KC2s, but it's the same thing.
Could you also do W times 1 over X squared? That's not simplified.
Yeah, but that's, no, it's the same thing. And the other thing, the other way you could see it is like this, right? Could you see it like this?
Yes.
Yes. So just be careful because you never know what form you're going to get it in. All right?
Because 1 squared is 1 is 1. No, yeah, I didn't know what you said. I thought you meant W over X. That's what I thought.
All right. You're good?
Yeah.
All right.
That's what I
Sounds
thought
good.
you said,
Now, some equilibria involves gases only, and when you get equilibria that involves gases only, you're more apt to use KPs, where you're dealing with partial pressures of substances. You write it very, very similarly. It says, in reactions involving gases, it's often easier to measure partial pressures than molarities. The equation is given. Again, products on top, reactants on the bottom. And instead of using those concentration brackets, those very square brackets, you're going to use parentheses where you have the partial pressure of gas G raised to the stoichiometric coefficient, partial pressure of gas H raised to its stoichiometric coefficient, partial pressure of gas A raised to its, etc. I do tend to see quite a bit of these lately as opposed to concentration. We'll do both types as we go, so you're very comfortable with anything that they throw at you. Now, this actually is very interesting because this is not an equation that they're giving you anymore. I still see it built in. Maybe something you want to put in the memory bank. A couple ways to remember it will make sure you're good to go there. There's a relationship between Kc, which is the equilibrium constant dealing with concentrations, and Kp, the equilibrium constant dealing with pressures. And last time I told you that there was a whole family of, oops, wrong notebook, a whole family of Keq, and now you're starting to see it broken down a little bit more, and that's shown right here. So in this chapter, in the equilibrium chapter, we're going to deal with Kc, Kp, and then those of course are equilibrium based, and Q, which is based on initial amounts, and the Pogel packet will delve into Q quite nicely, so I do recommend it. I know a lot of you didn't do the Pogel packet last time, and I think you regretted it in regard to at least the formation question, which really was quite simple. Is that mine too? Good try. I'm teasing. Upside down. You're cockeyed. I'll fix it. Don't shove it in. Go this way. All right. So there are a few things in the Pogel packet that really enhance things we've talked about. We'll get into this branch with acid and base. That'll be your most favorite of the whole year. And then we'll get into solubility, product constants, all right? So we're going to embark here, and off we go. Okay, so the relationship between Kp and Kc can be illustrated with the following equation, where Kp is equal to Kc times RT raised to delta N of the gas. So it becomes, what's delta N of the gas? Well, this is very simple. This is the change in the number of moles of gas as the reaction occurs in the forward direction. So delta N of the gas is going to be stoichiometric coefficients of gases in the products minus stoichiometric coefficients of gases in the reactants, okay? And we'll go through a few examples here. The way I remember this is CART. You know how to spell CART. K, not with a K, dopey. C-A-R-T. So I know the Kc piece goes with the RT piece. That's how I remember it. I'm not sure it's brilliant, but it works for me, so give it a shot. For example, given Kc of 1.8 times 10 to the negative 6 for the following reaction at 457 Kelvin, derive the value of Kp at the same temperature. Okay.
On the cart part, where'd the A come from?
There is no A.
It's Kurt.
Do you want a carrot? Like a girl's carrot, carrots and diamonds?
Okay.
I don't know. I used to play a lot of golf. Carts made sense to me. Down here, they're always in carts at schools. That's how the police officers get you. So, cart. Come up with something more.
They're like a shopping cart.
Yeah, me too.
Doesn't matter. My parents owned a supermarket growing up. I never went food shopping. Now I think it's fun.
You like food shopping?
I think food shopping is great. Let's get back to the task at hand.
That's R. Which one is it?
Say what?
The R. Is it 8.3?
It's the 0.0821. Yeah. So
I don't
careful there. Right. In the previous one, we were all over the 8.314, although some of you came up with very interesting values for R. And then here we're at 0.0821 liters atmosphere mole Kelvin. All right. So, a lot going on in this problem. First thing we need to do is compare the two reactions. What happened from the reaction highlighted in yellow to the reaction highlighted in blue? We switched the order and we multiplied by 2. So we're going to take the reciprocal and raise to the second power. So that's what I illustrated here. The first thing we had to do was get the new Kc, if you will.
Oh, we divided them. I was going.
Well, you flipped it, reciprocal, right?
Yeah, I was going.
It's from blue to yellow.
So see how nitrogen dioxide's a product here, and yet it's a reactant here. So we had to flip, and we squared it because we multiplied by 2.
Wait, so
No, but we're not squaring it. We're dividing by 2.
Can you not go from yellow to blue?
Oh, I'm sorry. From yellow to blue, we didn't multiply by 2. We multiplied by 1/2.
Yeah.
Okay.
All right. Sorry. 1/2. Does that make sense?
Yeah.
Should we do it again?
Yeah.
Good. Okay. 745. Now, that's my new Kc piece that's going here. The R value, the temperature in Kelvin, so they cancel. The delta N of the gas. Now we're going to focus on the blue equation. We've got 1 plus 1/2 is 1.5, or 3/2. 1.5 minus 1 is 1/2. And that's why we have 1/2 right here. Ooh, we'll do another one, don't worry.
Wait, what?
The delta N of the gas is the sum of the coefficients of the gaseous products, which is 1.5, minus the coefficient of the gaseous reactant, which is 1. So that's where this 1/2 comes from. That's the delta N of the gas.
Is it a product 1.5 minus 1?
3/2 minus 1 is 1/2.
It's 1.5.
3/2
Yeah. I know. So I'm
minus
saying
1.
if you subtract 1 by 1.5, you get it.
Well, you do product minus reactant.
Okay. That's what I said.
Yes?
Product minus reactants.
So 1.5 minus 1 is?
1.5. But you said 1
No,
minus
1.5 minus 1 is 1/2.
Yeah. But I thought you were saying 1 minus 1.5.
No.
Okay.
Products minus reactants.
Yeah.
Almost everything's products minus reactants except bond energy,
Which is reactants minus product.
which is the other way, which some of you got confused on the quiz. Okay, now, one other key point to make, so you get here. Now, looking at the formula shown here, anything to the first power is
The thing.
the thing.
Yeah.
Anything to the 0 power is 1. So if delta N of the gas is 0, then RT to the 0 becomes 1. And in this case, when delta N of the gas is 0, then these two quantities are equal. Okay? All right. So we've talked about when you change the order, you take the reciprocal of the K. If you multiply the equation by some factor, you then raise its Kc to that factor. And to get the net equation, do you add the Kc's or do you multiply? Multiply. And then the relationship between Kp and Kc is shown. And before the exam, we'll go over any formulas that you really need to commit to memory because they're not provided to you. Now, I'm going based on the formula sheet that the kids used last year. Every year they throw something on there that wasn't on previously. So if you see something on there that you're not accustomed to seeing, goody goody, and just keep moving. All right. Equilibria involving pure solids and liquids, and this is going to come back to your question that I said we would address in more detail. If you have a reaction in which only gaseous reactants are present, you have a homogeneous reaction. If not all the reactants and products are gases, you have what's known as a heterogeneous reaction. Equilibrium constant expressions do not include solids and liquids because their concentrations do not change in a reaction, which is what I had stated earlier. So if you write the Kc expression for this decomposition reaction, what you're going to do here is you're not going to include the solids for the reason indicated, and Kc is equal to the concentration of carbon dioxide, or Kp is equal to the partial pressure of carbon dioxide. And some of you should be thinking, ooh, partial pressures, we learned that in gases. So that could be a linkage type question that you might see on the next quiz. So this is where you're really going to have to be careful because you've learned a lot already this year and the best is yet to come. You've got to try and make these linkages now, okay? So that may be a hint. I didn't write your quiz yet, so you never know. But now I've thought about it, so I'll try and make it work. All right. It says the reaction of steam with iron is an old method of producing hydrogen gas. So steam and iron. Write the KEQ expression. You want the Kc and Kp. Take a minute to write the Kc and the Kp for that problem.
Is there a speaker on or something?
I don't know. Do you want to turn? My
No,
volume's
it's that.
off. Oh, no, it's on. No, it was off.
It's that.
Oh my gosh.
No, I
Concentrate for
can't, I
more than a
can't.
nanosecond.
The noise.
You guys are goofballs.
I stopped listening for the last minute because all I heard was this noise. Guys, listen. I'm not gonna do it.
Do your problem. Stop wasting time.
I can't. Yeah. It was so annoying. Have you always had that whole thing?
That's where the camera is watching you. Well, they're sort of the same.
They have one has brackets,
One just
one has
parentheses,
parentheses.
one bracket.
I got it correct.
Now, would Kp be equal to Kc in this problem?
Yeah.
Yes, it will. Because the delta N of the gas is?
Delta N is 0. 0.
Because it's 4 after the 4.
The book I want is under the stack. I've got to go get a new one.
Why is that?
Yeah.
Oh, because 4 moles are being used and then 4 moles are being created.
4 minus 4. 0.
Yeah, but don't you do it?
0.
All right. So there was a problem I must have wanted to check out in the book. So let me grab one.
I get it. You're only subtracting the 4 of the gases for in the reaction.
What number did I? What page? 631?
Yeah.
Okay, so I had said we were going to look at 26. Let's take a look. Probably not super easy to see. It says at high temperatures, elemental nitrogen and oxygen react with each other to generate nitrogen monoxide. Suppose the system is analyzed at a particular temperature and the equilibrium concentrations are found to be. Oh, that's just an easy problem to do. All right, so where do we begin?
Make the equation.
Absolutely. What? Not the expression, right?
So NO squared.
Huh? Oh, okay. So Kc is equal to the concentration of nitrogen monoxide squared over.
Concentration of nitrogen, concentration of oxygen. The first multiple.
Now, years ago, that's how your part 2 started off. You were like, yes. Now they torture you. Okay.
Who's they?
Okay. Now, the concentration of nitrogen gas is 0.041 molar. What do you mean you can't see? Ah, can you see? That's because it's so big. Is that better?
Well, now we can't see the question.
Well, I'm going to read you the question anyway. All right. And the concentration of oxygen gas is 0.0078 molar, and the concentration of nitrogen monoxide is 4.7 times 10 to the negative 4 molar, and we want to calculate Kc.
Oh, that's it?
Go!
No, you just do it.
Of course it's easy.
Of course.
Chemistry. It's just math.
It's just
Easier than calc.
that's math. What is easy to count?
All right. Are you done?
No.
What'd you get?
1.4.
Something wrong?
That's not what I got.
6.9 times
6.9.
10.
Oh, wait, hang on. Looks like I missed a key.
Oh, wait, sorry, never mind.
You missed a key too? All right, what'd we get?
6.9
Times 10 to the negative 4 I got. 4. Who forgot a 0? Did I forget a 0?
I forgot a 0.
Okay.
I got it.
The other point I want to make, and I don't think I mentioned very much of this the other day, is we do not use units for Kc or Kp. Kc and Kp units are dependent on the equation, so it gets very, very complicated. In this particular equation, the units would cancel anyway. For simplicity, chemists do not use units for Kc or Kp. Keep it simple. Why would Kc be equal to Kp in this particular reaction? Because delta N of the gas would be 0 here. Exactly. Gases, gases, gases. The other problem is 44, which I would like to look at as well. Number 44 says that this reaction has a Kp equal to 109 at 25 degrees Celsius. It says the equilibrium partial pressure of bromine is 0.0159 atmosphere. The equilibrium partial pressure of this substance is 0.0768 atmosphere, and they want to know the partial pressure of nitrogen monoxide at equilibrium. Take a few minutes to get that down and give it a shot. And I'm going to re-emphasize the importance of doing some practice problems. Some of you think you remember all of this from last year. Some of you have never seen this before. And practice problems, you did KEQ. It's going to be grossly similar. Practice problems are going to go a long way to helping you be successful here. And then there will be 2 little sections I would like to do. We'll take a break. I'll go over Le Chatelier's principle, and then we'll have some practice time. That will leave us with a short lesson, but critically important on Friday with a lot of practice. And we will lab it on Tuesday.
The test is Friday.
Quiz
Or quiz night.
Friday. And unfortunately, your quiz spans the weekend with period 2. I'm sorry.
Wait, are we on Friday
This
or
Friday?
lab?
The lab will be Tuesday, Wednesday.
We're doing another lab?
Yeah.
Oh,
Are we done with this?
The quiz is this Friday or next Friday? This Friday.
Unless I give you a surprise quiz on Friday.
This Friday? No. I meant next Friday. I'm already on to next week. Great.
What'd you get?
5.83.
That's what I got.
5.83 times 10.
Atmosphere.
But why did you need to use R and T for anything?
Because I didn't ask for Casey, but that's a good question. So if given KP here, you could ask for KC. You know KP is equal to KCRT. There's your cart, delta N of the gas. And you could do it that way. What would delta N of the gas be here? -1. and we're given Kp, so we want to go after this piece.
So you would multiply KP by 2?
No, you would do, I see what you're saying, yeah, you could. Kc is equal, you did 2 in your head, I'm going to do it simpler. But yes, you are absolutely right. Now we know delta N of the gas is -1, so Pedro's like, oh, well then we can just fling this up here, and that is correct. If you didn't see it, you can plug and keep going. Your Kp here would be 109. Your RT, here the R is 0.0821. I'm going to be a little lazy on units here because they're not even going to cancel, so who cares? The temperature is 298 Kelvin, and this whole piece is to the -1. And so Kc here would be, how many siggies we want? I'm getting this initially, but we only want 3. Actually, you could get down to 2 if that truthfully was the temperature, since it figured in. All right, so you could easily whip that through. The other thing we want to be able to do here is we want to be able to interpret values of Kc or Kp. Typically, you're going to be off Kc for interpretation, but maybe not always. It says that a very large value of Kc or Kp is going to indicate that the reaction essentially goes to completion. It's not reversible, only going in the forward direction. So double-digit powers of 10, so like to the 10th, the 11th, 12th, etc. So if you have a Kp value that's as ginormous as that, essentially reaction's only going in the forward direction. A very small value of Kc or Kp signifies that the forward reaction as written doesn't really occur to any significant extent. This is going to be 10 to the -10th, -11th, etc. But when you're talking about equilibrium constant expressions, you're talking about reversible reactions at equilibrium. And we'll link a little bit more here in a minute. Keep in mind that when you're talking about determining whether a reaction goes, there's 2 factors to consider. Is the reaction thermodynamically favorable? That is, does it have a negative delta G? And is it kinetically favorable? And when you're dealing with kinetics, you're looking at the speed. Is the activation energy easily overcomable so that the reaction goes in the forward direction? And I think, let's do this piece and then we'll take a break. The other piece I want to mention, this is going to be brand new. It's going to be critically important. We're going to introduce Q here, but we're not going to come back to it until next time, but that's okay. So it says the reaction quotient Q, and this is going to help us predict whether the reaction is going in the forward or the reverse direction. Okay? So Q sets up identically to Kc or Kp, but now you're under non-equilibrium conditions. For the most part, you're going to be under initial conditions unless you do something to a system at equilibrium. So for the most part, Q is going to go with initial conditions, initial concentrations, or initial pressures. It's not going to be constant for a reaction the way KEQ is. You can predict whether the reaction is going in the forward or reverse direction in order to establish equilibrium. There are 3 situations. If QC, and that's going to be calculated from non-equilibrium conditions, typically initial conditions, is less than Kc, then the reaction proceeds in the forward direction. So the rate of the forward is greater than the rate of the reverse reaction. That's because you haven't reached equilibrium yet. You have more reactant amounts than you do product amounts. If QC is greater than Kc, Now the net reaction is going to go in the reverse direction. Greater, reverse. And when they're equal to one another, we say the reaction is at equilibrium. This concept's not going to come together till next time, and that's fine. You could calculate Q, though, and you could figure out which reaction is going to proceed, that is the forward or reverse. For example, it says in which direction would a net reaction occur if the conditions for the reaction below were. These are not equilibrium concentrations, but rather initial. An initial concentration of hydrogen iodide of 1 molar, initial concentrations of the products at 0.1 molar. The Kc is given. To calculate Q, you write it exactly the same way, but these are not equilibrium concentrations. Rather, they're non-equilibrium. In this case, initial amounts. Equilibrium hasn't been established yet. Plug in the values and solve. Here's my QC. Here's my KC. This value is clearly less than this value. And when it's less than it, the reaction proceeds in the forward direction in an effort to establish equilibrium. If Kc is greater, then the reverse reaction is favored to get back to equilibrium conditions. The Q concept will be made clearer next lesson, not today, but next time, and the Pogel packet's going to touch upon it as well. I'm going to take a piece at the Pogel packet. It's probably too much for right now. It's probably good after we have finished the other piece of the chapter, the major other piece for Friday. But if you know you're not going to be here Friday, that's why I think I'm going to hand them out today, but you probably don't want to touch it till after Friday's lesson. We're going to take a short break, and then we will introduce Le Chatelier's principle. For those of you who have seen it before, it's grossly similar with maybe a little bit of new stuff. It's very, very, very simple if taught well. Hard to read from a book. So we'll take a short break. Hopefully you have a better understanding of Kc, Kp, how to write, how to calculate. You need some additional practice for mastery.